Start the recording. So again, I will repeat this for an whenever we draw the MOSFET as a three-terminal device. Okay. Whenever we draw the MOSFET as a three-terminal device, the inherent assumption is that the body is either connected to the lowest terminal, lowest potential of the circuit, or to the source in case of an NMOS. And in case of a PMOS, the body can be assumed to be connected to the highest potential of the circuit or to the source. Either of these two are valid, and the input output characteristics will be drawn. So there are two variables here, input control, two controlling variables and two monitoring variables. Okay, you are going to monitor the drain current and you could vary this. So that means it becomes a three-dimensional plot and it is difficult to interpret or understand from there. So what we do is we keep one of them constant and vary the other one. So in case of ID VDS characteristic, we keep the VGS constant at VGS1 and vary the VDS. Initially it will be in triode region and then it will get into saturation. Then as I keep increasing VGS, the current is going to keep on increasing, and once it hits saturation, it will be this. It will stay constant at that point. Now this dotted line is the boundary between triode and saturation, and this dotted line will follow the VDS equal to VGS minus VTH, and this will follow a parabolic curve at that point. So I would ask you later on to probably prove why this is like this. Okay, because at the point when it hits saturation, sorry, at this point and at this point, at this point, and this point, what is the current equation? ID equal to VGS minus VT square. So here it is VGS2 minus VT square. Here it is VGS3 minus VT square. Here it is VGS4 minus VT square. So therefore ID versus, if I consider VGS as the x-axis, this will be a parabola. Okay. So channel condition VGS is greater than VT, there is an induced channel at the source end. VGD greater than VT, there is a continuous channel all the way from the source to drain. When VGD less than threshold, less than equal to threshold voltage, pinched off channel. Okay, so I have already explained this. I have just written it in an explicit manner over here. And the expression for currents are triode region. This is the exact expression for current. Saturation region, this is the expression for the current. And when VDS is very small, okay, with then VDS square can be ignored, then it is called deep triode or resistive region. So resistive region, this is also another name for this is deep triode region. Okay. So that is this is obtained from the last term is obtained by neglecting the half VDS square term. Okay. Now one important terminal boundary between triode and saturation region is a parabola given by this. Right. So as I have already explained that it is going to be a parabola given by this, and this thing, the boundary between triode and saturation is also called the edge of saturation. Edge of saturation means VGD is equal to VTH. Means pinch off right at the drain. Exactly at drain. Okay. So this is an important term in the exam questions. I might ask you now, what is the current when the transistor is at the edge of saturation? So edge of saturation, the condition is this. Okay. This is edge of saturation VGD equal to V threshold. Am I clear? So now we will draw something. As a circuit designer, we have to draw the thing transistor not as a symbol, but more in terms of the circuit parameters. Now, whenever we are analyzing a circuit, we usually do two analysis. Okay, one is large signal analysis, and then the small signal analysis. Okay, this large signal analysis uses exact current voltage equations. Exact current voltage equations. This uses linearized approximations. Okay. So as I said, the large signal model of the transistor in saturation, okay, is it behaves like a current source between drain and source, and the current is given by this. It's an exact CV current voltage characteristic, and between gate and source, it is acting like a capacitor. Okay, and this is the condition. Now let's take an example. If I have this circuit, calculate the bias current flowing through this transistor. If so how do you calculate this? So I have a voltage 1 volt here. Okay, gate source voltage is 1 volt. I've given the threshold voltage is 0.4. I've given you the aspect ratio over here, and we have given you the process transconductance parameter. So what is Kn here? Kn equal to 100 microamp per volt square times 2 by 0.18. This is the Kn, because Kn dash is this. Kn is equal to Kn dash times the aspect ratio. Now, if you are given this, calculate the bias current of M1. Can anybody tell me what should we do here? You guys have already done this. So let's get one of you to suggest how to solve it.
Make the saturation assumption, and we know that VGS is a constant and it's equal to 1 volt. Find the value of ID, then just confirm if VDS is actually greater than VGS minus VT.
Okay, good. So yeah, I hope everybody got that. So basically what we do is, so we'll say assume M1 in saturation. Okay. If I assume M1 in saturation, then ID equal to Kn 1 by 2 Kn VGS minus VTH square. Okay. So I can then solve for ID. Once I have solved for ID, I can find this drain voltage. And once I found out the drain voltage, I'll see if the transistor is in saturation or is it in triode. If it turns out that the transistor is not in saturation, then what do? We plug in the expression for the ID equal to, I write ID equal to VGS minus VTH, then VDS square, my VDS minus half VDS square, we write it like that. Now it's a quadratic equation. We solve for that quadratic equation and obtain the VDS. Okay. So and once we do that, then we can then we say that it is so it comes out in triode region, and once it is in triode region, then we solve for the VDS using the triode region equation. Okay, and that's a quadratic equation. One of the solutions will be a valid solution, and the other solution will be either greater than VDD or less than 0, because those it cannot be, the voltage at this point cannot exceed 1.8 volt, cannot be below 0. So when you solve the quadratic equation, which is needed when you are solving the triode equation, that time you will get two solutions. One of the solutions will be the valid solution, and the other solution will be an invalid solution, because it will be either greater than VDD or less than 0. Okay. Now, if gate voltage increases by 10 millivolt, what is the change in drain voltage? Okay. So in order to do that, so as I said, let's assume M1 is in saturation. Then ID is given by this equation. We solve for ID, we get 200 microamp. V out equal to VDD minus IDRD. So this turns out to be 0.8 volt. Is M1 still in saturation? If this is 1 volt and this is 0.8 volts, is M1 in saturation or triode? Is there a channel at the drain end?
Saturation.
Yes, because there is no channel at the drain end, because gate minus the drain is 0.2 volts, which is less than the threshold voltage. So there is no channel present at the drain end. Now, if VGS increases by 10 millivolt, then new VGS is 1.01, correct? So ID will be given by this current, this value here. Again, assuming it is in saturation, and we'll confirm that it is still in saturation. We get this, fortunately it is. So change in V out is 34 millivolts. Change in V in is 10 millivolt. So therefore, we have an amplification. We have amplified the signal. I gave a 10 millivolt change at the input. I got a 34 millivolt swing at the output. So we have built an amplifier. Okay. So how does this amplifier work? Now let's look at it very closely. So what is the principle of operation of the amplifier in this scenario? You change this voltage. What does it? What is the effect of this change in voltage? It changes the current. Okay. This change in current is made to flow through a load resistor to give you a change in voltage. So if you have a voltage in voltage out and you want to realize that using a transistor, it is a two-step process. So voltage to current conversion, and then current back to voltage conversion. So your voltage to current conversion is done through transistor. Okay. Current to voltage conversion is done through a resistor. And this current to voltage, this resistor is also called a load. Okay. Am I clear? Any questions? Okay. Now, as I had told you earlier, so voltage change gives a current change. The change in current flows through a resistor, giving change in the output voltage. So this is a two-step process. You change the voltage. If I want a voltage output, sometimes we want current output. We want a current amplifier, voltage to current conversion. That time we don't need to make it flow through a resistor. We get the current. Okay. And sometimes we want a current input and a voltage output. That time we'll do something else. And sometimes we want a current input and a current output. We'll do something else. We'll discuss all these different amplifier topologies, which are voltage in, voltage out, voltage in, current out, and current in, voltage out, and voltage in, current in and current out. So this is a voltage amplifier. The gain is dimensionless. This is a transconductor. So let me write it here. So voltage in, voltage input to voltage output. Output short form, I'm writing it as like this. And this is a voltage amplifier. Amplifier, AMP is the amplifier short form, and the gain is dimensionless. Now we can have voltage input. I'll shorten the input as IP, and we can have voltage output, resulting in a transconductor amplifier. These find all different, then we can have current input.
So there will be current output in the second one.
Oh, sorry. And current input and voltage output. This is a trans resistor. And current input, current output is a current amplifier. So current input, voltage output is what you use in your optical fiber receiver at home. Okay, the optical fiber signal is coming in light domain. The light is converted to electrical current. So through an LED, LED burns a current. That current gets amplified to generate a voltage, and finally you are able to see. Those of you who have an optical connection at home, you can see this geo fiber might be there. You will have something called box at home, which optical fiber is coming in, and then you can you are finally getting the signal that you are getting. Okay, does anyone have any optical fiber connection at home over here in the class?
Yes.
Yeah, please go and check there. So there is an optical cable coming and that goes to an LED. Okay, voltage input and current output is what happens is that when I'm transmitting a signal into the optical fiber cable, I'll pump in a current to the diode. Okay, so the voltage will be an input, the signal voltage that gets converted to current, that LED diode, that light is then transmitted to the optical fiber. Okay, so modulate the current flow, light intensity on the LED using that this thing. Current input and current output. There are a lot of applications of current amplifiers where you want to amplify the currents. So these find a huge amount of application there. Okay. A voltage amplifier and current amplifier, these are dimensionless. This has the dimension of 1 over ohms, and this is ohms. This is dimensionless. Dimensionless. And this is also dimensionless. Now, why do I bring in this dimensionless thing? Whenever you are solving any problem in the exam, please make sure that your dimensions make sense. If they do not, that means you have done something wrong. So do a dimensional analysis using the dimensions, and if the results are matching, okay, then your result might be correct. Not necessarily that it will be correct, at least that it should be dimensionally correct. Okay. So now I had told you what value of W over L places M1 at the edge of saturation. Now, what is the definition of edge of saturation? This means VGD equal to VTH. Channel is pinched off right at the drain. That's the definition we said. So that means this voltage is 1. Okay. So this voltage is going to be this minus 0.4. This minus 0.4. So this is how much? 0.6, right? So therefore, now I have a resistor between 1.8 and 0.6 volts, so I can exactly find out the drain current. So once I know the drain current and I know the expression for drain current is ID, so drain current is ID at the edge of saturation is equal to 1/2 mu n Cox W over L V effective square. VGS minus VTH is V effective. So we know exactly V effective is how much. Okay. And we know mu and Cox. We know the current because we have defined the condition of edge of saturation. And therefore, I can find out W over L, the aspect ratio. Okay. Under what channel formulation at the drain end of M1. So VDD minus V out by RD is 240 microamps, and therefore WL max is given by this. Okay. Am I clear with this this example?
Yes, sir.
Okay.
Sir,
Yes.
in the previous example,
Yes.
so why would be the value of W by L maximum?
Okay. So what places, if I make W by L more than this, what happens to the current? If I make it more than this value, won't the current, now think of it this way. If I make this bigger and bigger, right? For the same VGS, it will pump in, take in more and more current, right? Yes or no?
Yes, sir.
As it takes in more and more current, what happens to this voltage?
It's gonna reduce. Yes.
If it it is going to reduce, then what happens to the mode of operation of the transistor? It is going to get into
Saturation.
if it reduces, it gets into saturation.
It's a
Triode
triode.
region.
Triode, sir. Triode.
Yes, triode region. It gets into triode region. Now, once this, so that means if what is the maximum value of W over L at which it will maintain at saturation? Am I clear? So that's why we call it as the maximum W by L max. Does it answer your question?
Yes, sir.
Next thing is the channel length modulation. Okay. So as I said, as the drain voltage at VGD equal to threshold voltage, we have pinch off right at the drain end. Okay, pinch off will happen right at this point at VD, and we call that as VD sat, and that's why we give it a name of VD sat. VD sat is the voltage at which it is at the edge of saturation. Okay. So minimum voltage across the drain source, which makes sure that it is at it is in saturation. Am I clear? That is the definition of VDSAT. If VDS increases beyond VDSAT, the channel pinch off point moves towards the source, so it keeps on moving, because at this point now VG minus this voltage will become equal to threshold voltage, and therefore there cannot be any channel. This at these points it is going to be less than threshold voltage. There cannot be any channel here. The additional voltage greater than VDSAT drops across the depletion region between the end of the channel and the drain region. Between this and this, VDS minus VDSAT drop is happening over here. Is this figure clear to everyone? Is this clear to everyone? Now all of you please have a pen and paper with you. Okay. Of course, I cannot see you, but at least I would suggest that you have. Is this figure clear to everybody that this between this and this, the voltage difference between here is VDS minus VDSAT? Is this clear? Why is the voltage difference over here equal to this value?
So because at L minus del L, VDS is VDSAT.
Exactly. At
So
this point,
VX is VDSAT.
Vx is VDSAT. Okay. Drops. So therefore, my electrical length of the transistor becomes L minus delta L. Now I know current in saturation is equal to ID is proportional to 1 by L, and now this L is known as electrical length. Okay. Okay. So, however, with widening depletion layer, the effective channel length reduces from L to L plus delta L. So this electrical length is also called as, I would say, the effective channel length. Okay. It is called the effective channel. This change in channel length is called channel length modulation. That means your drain source voltage is now modulating the electrical length or the effective channel length of the transistor. Now we know that ID is given by this. ID is inversely proportional to the channel length. ID increases with increase in VDS because this thing comes in the denominator. Okay, so now I can rewrite this drain current as I can take L common out of here. I can take L common and we have 1 minus delta L by L. Okay, so up to this point it's clear, everybody? Okay. So if I Taylor series expansion of 1 by 1 minus x equal to 1 plus x if x is very, very small, much less than 1. Okay.
Sir,
yes.
Sir, if L decreases, why does current increase?
If L decreases, so in the current decrease or increases?
Increase.
L decreases, the current will increase. Yeah, because L is in the denominator.
But I am saying that suppose the current is actually going from source to drain, the actual geometric distance is still the same.
Okay. But
so how does the channel actually play the role?
No, the thing is that it is so basically what happens is that the when we do that when we find out that current is what dq by dt, right?
Yes, sir.
Right. So now the current is going to increase if I reduce the time or I increase the rate of change of charge. Correct?
Yes, sir.
Now, what happens is that when you change the channel length, the thing goes through the effective channel length through that it is going through a drift, and after that it gets sucked into the drain. So effectively, there you can say that the time, although the distance is L, the time when it is going from the edge of this point from here to here, okay, it is not like it is mu times E at that point. That is what I think is the reason why the current will increase. Because here when it is flowing, it is a mobility times the electric field. Okay, but from here to here, it transits much faster. Okay. I do not have a device explanation that way. Okay, so physically, I would say that the channel length reduces and therefore the current is going to increase.
So
somewhat
sir,
answers your question, right?
Sir, we can actually get the expression of how fast the electron drifts, electron is moving in that region, because we already know how it varies with the length, so we can calculate that.
We have the current, the velocity of the electron is mobility times the electric field, right?
Yes.
But that is the drift velocity, correct? So yes. Drift velocity is happening when that thing is drifting through because of in the conducting thing. in a conducting plate. Now, and the depletion region, when it is getting sucked into that, I don't think that that expression holds at that point. Okay. So I'm not sure of that. So I don't want to misguide you guys, but from a circuit perspective, the expression for current has L in the denominator. And as I change the drain source voltage, the effective length keeps on reducing, and therefore the current would keep on increasing. Okay, so keep in mind the expression for current that we have derived, where is it? So expression of current that we have derived is based on this. Okay, this is the drift velocity, and drifting is happening in the channel. Correct? After the channel, when the channel pinches off, there it is no more a drift velocity. So there is something else happening at that point. So the electron gets sucked in. So this expression is no more valid. So this expression is only valid in that wherever the channel is present. Am I clear?
Sir, so can we say that we calculated how the resistance varies with the length previously? So can
No,
we
but
say that
keep in mind it is not a resistor. A current source is not a resistor. You cannot see. Can you apply KVL? If I have a network and a current source is in a network, okay? Okay, and I have a voltage source here also. Can I apply KVL in this loop?
No.
Huh?
No.
Yes. Why not? Because by definition, this can behave like a current source for any voltage across it.
Yeah.
So I cannot apply KVL in the current source. Okay. Similarly, I cannot apply this voltage source sink in any amount of current. Correct?
Yes.
So that is what we have to be careful of when we are what we are using. So keep in mind this expression for the current that is flowing through the transistor is defined in the channel. Am I clear?
Yes,
now,
sir.
if you specifically want how it behaves in that, in between that, I'm not a devices guy and I don't want to misguide you. Okay,
Sir,
there is
but
one
current
person.
is same through all the cross sections. So whatever it is in the channel, same should be in that depletion region as well.
Exactly, it will be the same, right? But the current flowing through the channel is defined by this expression, right? Eventually, finally, it is defined by this expression, or in saturation, it is defined by this expression. Okay. Now, if I, as per this expression, if I keep changing the channel length, what is going to happen? Your drain current is going to keep on increasing. Am I clear? Does it make sense or no?
Yes, sir. Sir, can we say that we are maintaining the same voltage across both the ends of the channel, and as we are decreasing the length, we are increasing the electric field?
Perfect. That's a very, who is this guy?
Sir, Vishwabasu Roy.
That's a very good way of saying. Okay, I'm glad that you said it that way. Very nice. So what he said, okay, say it from here. So this voltage from here to here is the same, correct? If this keeps on moving, if this point moves here, that means I have the channel like this, then the current is going to be, this difference between these two is still the same, correct? So Biswabasu, please say it in your words. I like the way you said it.
Exactly at the source and at the point where we are having that pinch off, between those 2 points, voltages will be same whatever be the length of the channel. Now,
exactly.
If the channel length decreases, then we will have a higher electric field inside the channel. So the electrons will be drifted faster through. So we will have higher current.
Right. Does it make sense? I'm glad that you said it that way.
Yes, sir, it makes sense, right?
Okay. Good. So good learning for me. So I think I should write it down. And I can say it that way in the next future classes. So, okay. So now, where was I? So we were over here. Okay. So ID, therefore, in the denominator, we know the Taylor series expansion that all of you know about this. So we will have an expansion given. Therefore, the 1 by 1 minus delta L by L will turn out to be 1 plus delta L by L. Now we say that we say that delta L is lambda dash VDS. We define something because see the delta L amount of reduction in the channel length. We can define a constant and say that with respect to that, as VDS is increasing, lambda times that much it is reducing. Where lambda dash is a technology dependent parameter. It is specific to that technology. Therefore, we can say that VGS minus VT is given by 1 plus lambda VDS. Now, what is lambda? Lambda equal to, so if delta L is lambda dash by VDS, lambda equal to delta L by L. Sorry, it is going to be, we'll have, yeah, it will have a factor of L over there. Okay. So lambda dash by L, where lambda equal to lambda dash by L. So after the transistor has hit saturation, I have exaggerated the plot here just to make sure that I can have a reasonable point where it intersects. Okay, so that's why I've exaggerated it a lot. So what happens is that after saturation, beyond this, ideally it should stay like this. Okay, ideally it should stay like this, and ideally it should stay like this. Okay, it should stay like this. But it has a slope because of channel length modulation. And if for any transistor, if I extrapolate this, this intersects at a point which is equal to minus 1 by lambda. We're coming from the basic equations. Okay, you can solve it and find out where it hits 0. VDS equal to at what point it hits 0, it will be minus 1 by lambda. Okay, and this is similar to, we call it as VA, because this is a phenomenon that James Early, I think, he saw it in BJTs. Now the difference between this voltage in case of a BJT and a MOSFET is that in case of a BJT, this is a physical value. This has some significance. It's a constant. But in case of BJT, if I change the transistor, this value is going to change. Now, why did we do this? Because we wanted to, in this course, we wanted to use similar models, exactly similar models from circuit perspective to analyze both BJT and MOSFET circuits. Okay, both BJT and MOSFET work on two different physical principles. Okay, physics are different, but from a circuit's perspective, we can treat them almost identical because we can develop a unified model for them. Okay, so again, this VA, which is called the early voltage, has no physical meaning. It is not a constant. It is just a visualization for this thing, and correlating this plot with respect to BJT. When we discuss BJT, we'll also see a similar plot. Okay.
So,
yes.
So can you explain why are we taking del L is equal to lambda dash into VDS?
No, it is not that way. We want to see what do we want to do? We want to actual expression is this. Correct? Actual expression is this. Okay. Now, this is a device information. Now I want to relate that to circuits. So after I have done the measurement, I can say that when VDS is, I can always mention delta L in terms of this equation, right? After measurement of the transistor, and put that in the model parameter. That way the circuit designer doesn't care about what is L. He looks at the VDS and this technology dependent parameter and says that, okay, you know what, I'll use this. You want to translate a device parameter back into a circuit level parameter. What are the circuit level parameters? This, and this. So you have 1, aspect ratio 2, VGS 3, and VDS 4. These are the things you can control as a circuit designer. Okay.
So basically, VDS at saturation region, VDS would depend linearly with ID. That's why we can relate that del L and VDS are linear.
Yeah, and kind of like that's a proportionality constant, I guess. Like
That's a
yes.
proportionality constant. Yeah, that's
So
just
like
yes.
VDD minus ID into that R would be VDS. Like so we
Right,
can
right.
relate
True,
that.
true. Yes, yes. That is the reason. Yes. Okay. Okay. So again, I am stating it here. Voltage VA is usually referred to as early voltage after James Early, who discovered a similar phenomenon for the BJT. VA is a hypothetical number, as I mentioned. Okay, is a hypothetical number for MOSFET. Number obtained by extrapolation for MOSFET. Okay, this is for MOSFET, but is a true number for a BJT. If current changes with voltage, there should be a resistance associated with it, right? If my current is changing with respect to the voltage, then there is a resistance associated with it. Am I right? Between the drain and source. And therefore, I can define the resistance between the drain and source is nothing but VDS by del IDS, right? For a particular VGS. And that turns out to be equal to the output resistance of the transistor is equal to given by this. We would mostly be using this expression. Okay. This is what the BJT will give you. So we have, so that we can have a unified model for the BJT and a MOSFET. See, when we will be in this course, as I said, we'll be discussing amplifiers. When we get to, after we finish the MOSFET physics and the bipolar physics, we won't do an analysis of BJT amplifier and then a MOSFET amplifier. We will do analysis of amplifiers, both of them together, so that we, because they are from a circuit perspective, the terminal characteristics and all those things can be abstracted into circuit parameters that they both look almost identical. Okay. So RO is where ID is the drain current without channel length modulation. So therefore, the large signal model now will get refined to this. Okay. Before we had only this parameter. Now we are adding in the output resistance because the current is changing because of channel length modulation. And this RO is a function of the original drain current without channel length modulation that was flowing. Okay. So if I increase the drain current without channel length modulation, then my RO is going to reduce. Okay. As per this expression. Okay. Now let's try to visualize channel length modulation. So you can see that there is at this point the pinch off is happening close to the drain. As this keeps on increasing, the pinch off point keeps on moving over here. Okay. Now one important thing that I want you to remember here is the amount by which this moves is a function of VDS. If this distance and this distance is larger, if I have a longer channel versus a shorter channel, then delta L by L here is greater than delta L by L over here, because delta L is the same, but so here it is delta L by L1, delta L by L2. So this is going to be, so the longer channel devices will have a smaller slope versus a shorter channel devices has a larger slope. Okay. Larger slope here means smaller resistance, because the slope here is ID by 1 over ohms. Smaller resistance. So for that means the bottom line is for higher output impedance, increase channel length. Okay, that is the bottom line. So what is an implication from a circuit perspective? If I am an ideal current source, what is the impedance of an ideal current source? The ideal current source characteristic is I is over here, V is over here, it is slope is 0, means current impedance is infinity. Okay, so if I want to realize as a good current source, I have to approach an infinite resistance across the terminals for a current source. That means I should be using longer and longer channel lengths. Okay, a longer channel length gives me a better current source. Am I clear? So please keep that in mind. This is one abstraction. This is what a circuit designer is going to use. So next thing that I want to get into is the MOSFET, as we discussed, amplifies the signal or does any processing by first converting the voltage into current, and then the current is made to flow through a load or a resistor to get the final voltage output if it's a voltage to voltage. So the main action is actually conversion from voltage to current. So we have to define a parameter which defines the efficiency, how good is your transistor in converting the voltage to current, and that is measured by something called the transconductance. Okay, now the voltage to current conversion happens from the gate source voltage to the drain current. So therefore transconductance GM is given by del ID by del VGS. So this is kind of an efficiency of your transistor. We define this as efficiency of transistor. Okay, for transistor in saturation, we have this is the efficiency of the transistor. So you can see that if I want a higher efficient transistor, I should go for wider channel length, wider width, smaller channel length. Okay, this is in contrast to when I want to realize a current source. Okay, so when I want to realize use a transistor as a current source, I should have longer channel length because I want current to be current to remain constant. It should stay as this slope should be as small as possible. But when I want it to be an efficient voltage to current converter, I want to have lower channel length. Okay, so now there are conflicting requirements. If I want an amplifier, I want smaller channel length because it will convert more efficiently the voltage to current. If I want to really build precise current sources, because in the sometimes you want current sources, right? So that time you have to have longer channel length. Okay. Now, if I would suggest that you can use using the expression for current, which is ID equal to 1/2 mu n Cox W over L VGS minus VTH whole squared 1 plus lambda VDS now, right? This is the exact expression for the current. Now, using this expression, you could actually, for now, let us ignore the channel length modulation for the GM expressions for now. So let's ignore this. Okay, so in that case, using these two expressions, you can obtain GM expression like this and GM expression like this. These are two alternative expressions for GM. Now, why do we have this? Because we have to design circuits. Okay, so if I want to keep, when I'm designing a circuit, I can keep the current constant, some voltage constant, some terminal voltages I want to keep constant, some currents I might want to keep constant because power restrictions are there. So I would be using, when I'm keeping W by L constant, because area is a problem. W by L defines an area. If I want to not change the area of the device, and I can only vary the VGS minus VT, then GM is given by this expression. You can see that here W by L doesn't come into the picture. Sorry, not here. Here, W by L doesn't come into the picture. W by L constant is here, so I'm keeping that constant. It is a function. VGS minus VT is variable, so you can see that it is given by these two. When W by L is variable and VGS minus VT is constant, I will use one of these two expressions to define GM like this. So if I have to increase GM, then I will increase ID. If I have to increase GM, I have to increase W by L under this circumstance. Then under this circumstance, I can manipulate GM by using this property. So these are three interchangeable equations. So we can call this as equation 1 and equation 2 and equation 3. These can be obtained by substituting this and using these two expressions. Use these two expressions to solve / manipulate to obtain 2 and 3. So I can, with an example later on in, but this has to be done through simulations. So I don't want to get into difficult and tell you in theoretical way. So if I do it using LTSpice, if people are interested, we can show which thing I'm going to use on what scenario. So that will, let's see when I can get into the LTSpice experiments and all. Okay. So now what did we, so basically what from the physics model, we are now trying to get to a point from the physics of the thing. Now we have abstracted certain parameters of the transistor, and we are now going to draw the transistor from a circuit perspective. Then the physics part, we do not have to worry about. We should know the basic physics on what principle the current flows, okay, and how the current flows, and how the terminal characteristics are, what is the expression for current. But then finally we should be able to abstract that into a circuit parameter. For example, what we did is, just like in the large signal model, we found out that the current was changing. So then we abstracted that to a circuit parameter, RO. Okay. Similarly, we have got the transconductance, and then we'll discuss next week the small signal model, and we'll finish off the rest of it. So at this point, I think I'll stop now.